Welcome, ladies and gentlemen, to this video tutorial. Let's take a look at this question. This is exercise 5.4, number 1a. And we're being asked to plot the curve that is parameterized by this vector function r. So the domain is from -2 to 3 and maps into R2. So the image under R has two components, an x component and a y component. Okay, so instead of doing this by hand, let's do this using a computer. And specifically what I'm going to use is the Python package called SymPy. So what I've got open here is a Google Colab notebook, so you can find that fairly easily. Just Google for Colab. And what we're going to use is we're going to use the SymPy package. And in the SymPy package, what are we going to need? Well, we're going to want to solve equations, and we're also going to need the square root, and we're going to need some abstract symbol to work with. So from sympy.abc, that's the package that contains all the abstract symbols, we're going to use t. T because we've got a t in our vector function. Okay, so once we've got that, let us define the x component of our vector function. I'm going to store this in the variable rx, and that is t squared minus 4 times t. So t squared minus 4 times t for the x component. And for the y component, ry, that should be t to the power 3 divided by 3 minus t. Okay, so there we've got the x component and the y component of our vector function. We're also going to need the derivatives. So let's take the derivatives, and let's just use SymPy to do the derivatives. So d for derivative of the x coordinate of our vector function, sympy.diff for differentiate, and we're going to differentiate the x component towards t. And similarly for the y component. Okay. So here we've got our x components and our y components of our vector function and of the derivative of our vector function. Let's just check that we've got everything right. Our x is t squared minus 4t. Yes, that's fine. Our y should be t cubed minus t. Ooh, something is wrong here. Oh, I forgot to add here. That should be over 3. Okay. And our derivatives for the x component and for the y component. Okay, so far so good. I'm also going to just put these two components together. That will just make it a little bit easier if we need to work out the actual points on the curve that we're interested in. So I'm going to call this the r expression. So what is this going to be? This is just going to be the right-hand side of this definition of r. So, and I'm going to use a SymPy matrix. And this matrix has two components. It has the x component and the y component. And we're going to do the same for the derivative. And we're just going to put the derivative in there. So all that this does is it groups the components together. Okay, so now we've got everything set up, and now we can start working out the points that we are interested in. So when we want to make a plot, we of course need the endpoints, we need the x-intercepts, we need the y-intercepts, the vertical tangents and the horizontal tangents. And as we go along, what I'm going to do is I'm going to keep a summary of everything that we've worked out so far. Okay, let's start with the endpoints. So what I'm going to do is I'm going to take our expression and I'm going to substitute for t, we're going to substitute -2, or the left endpoint of what the values that t can take on. So from the domain of our vector function, just take the left endpoint, that will be our start point. So our start point has coordinates 12 and -2/3. So let's go to our summary. And this is of course the value for r -2, and has coordinates 12 and -2/3. So this is our start point. Let's add here start point. Okay, and for the right endpoint, so the end point, we're going to substitute 3. And we end at -3, 6. So this is our end point. So at 3, what were the coordinates? The coordinates were -3, 6. So -3, 6. And this is the end point of our curve. And now everything interesting is going to happen between these two endpoints. So let's put some space in there. And what I'm going to do is I'm going to write them in increasing order of the parameter. Okay. So our endpoints, we've computed them, -2 and 3. So now let's work out the x-intercepts. So we need to work out an equation. So we need to solve an equation, and for the x-intercepts, that is where the y-coordinate is equal to 0. So we need to solve the equation where the y-coordinate of our vector function is equal to 0. So here I've written EQ for equation, or y-coordinate is equal to 0. And that is of course when our y-coordinate is 0, those are our x-intercepts. And what we will now do is we will use SymPy. You can also do this by hand, but it's very good to teach yourself how to use a computer. So we will solve the equation where the y-coordinate is equal to 0, and we will solve for the parameter t. So the x-intercepts happen where the parameter is t equals to 0, minus square root 3, and plus square root 3. So let's go to our summary. Let's add this. So where r is, or where the parameter is equal to 0, we don't know what the coordinates are yet, but this is an x-intercept. And we have on either side, we've got at plus square root of 3, we've got another x-intercept, and at minus square root of 3. We've got another x-intercept. I'm just going to, for the moment, I'm just going to put off working out the coordinates of these functions. Okay, so let's move on to our y-intercepts. So y-intercepts are where the x-coordinate is equal to 0. So we want to solve an equation, and we want to solve the equation where our x-coordinate is equal to 0. That gives us our y-intercept. So let us solve this equation. SymPy.solve this equation for t. And we see the value of the parameter where the x-coordinate of our vector function is equal to 0. that is where t is equal to 0 or t is equal to 4. But we see 4 is not in the domain of our function. So we can disregard this 4, it's not in the domain. So our y-intercept happens where t is equal to 0, but we've already got t equal to 0, so this is also a y-intercept. Okay, and now we can immediately see that if the parameter takes on the value 0, we've got both a x and a y-intercept. So we expect this to be the origin. So the only point that is both an x-intercept and a y-intercept is, of course, the origin. So when we work out what the value of r0 is, we expect to get the origin here. It's always good to ahead of time make sure that we get what we expect. Okay, so we've got the y-intercepts, the values for the parameter to give the y-intercepts. We don't have the points yet. That's why I've got these question marks there. Okay, let's move on to the vertical tangents. We want to solve an equation, and the vertical tangents are when the derivative of our vector function has a 0x coordinate. So we're going to take the derivative of our function and the x coordinate and solve the equation where that is 0. SymPy.solve, and we want to solve this equation for t. And we see we've got a vertical tangent when the parameter t is equal to 2. So 2 is just slightly bigger than the square root of 3. So let's put them in order there. Here we've got a vertical tangent. Okay, and let's move on to the horizontal tangent. That is where the derivative of our vector function has a 0 y component. So let us solve for the parameters where the derivative of our vector function has a 0 y component. So the parameters have values -1 and 1. So let's put that on our summary. So -1 is between 0 and minus square root of 3. So here we've got a horizontal tangent. And at 1, we also have a horizontal tangent. Okay. So now we've solved for the parameters where all the interesting things happen, and now we can actually work out the points. So let us do that. So let us work out the coordinates of the point corresponding to the parameter minus square root of 3. So let's take the expression for r, and we substitute the parameter for t. We substitute the square root of 3 minus the square root of 3. Okay, and so that gives us the coordinates of this point. That is 3 plus the square root of 3, 4 times the square root of 3. And the y coordinate is equal to 0. And make sure that is what we expect, because this is an x-intercept, so the y coordinate is equal to 0. Let's also do plus square root 3. We also expect that to be an x-intercept. So that is 3 minus 4 times square root of 3. So that is that minus square root of 3. Okay. And again, 0 y coordinate because we expect it to be an x intercept. Let's take a look at r at, or when the parameter takes on the value minus 1, 5 for the x coordinate, 2 over 3 for the y coordinate. So that is 5 and 2 over 3. And let us just make sure, let's check the derivative, because we are expecting this to be a horizontal tangent. That means our y component of the derivative of our vector functions should be 0, and the x component should be non-zero. So let's just check that that is the case. The y component is 0, x component is non-zero, and that is what we expect for a horizontal tangent. Let's do the other one when the parameter is equal to 1. So the coordinates of the points on the curve is minus 3 minus 2 over 3. So here, minus 3 minus 2 over 3. And let's, for good measure, check the derivative as well. This is a horizontal tangent, so we expect the y component to be 0, the x component to be non-zero. And that is exactly what we get. Let's do r0, that is both x and y intercept. So we expect to get the origin if we plug in 0 for t. And in fact we do. So we get the origin there. So 0, 0. And what are we left with? We're left with this vertical tangent at t2. So let's substitute 2 in there. Minus 4, 2 over 3. So the vertical tangent point on the curve where we have a vertical tangent is minus 2, 2 over 3. Oh no, that is minus 4, 2 over 3. Minus 4, 2 over 3. That is where we have a vertical tangent. So let's just double check the derivative. What do we expect? We expect a 0 x component and a non-zero y component. Okay, so now we've worked out the coordinates of all the interesting points. We start when the parameter is equal to minus 2, we end it when it is equal to 3, and here we've got all the interesting points listed in order. So now we can use this information to make our plot. Okay, but we're not going to make our plot by hand. What we're going to do is we're going to use SymPy to make our plot. So if you don't know how to do something, Google is your friend. So let's see, how to make a parametric plot with SymPy. So that will take you to the SymPy documentation. Here is the SymPy documentation. There is an interesting function, plot parametric. And this, the documentation will tell you how to make a plot. So what do we want? Simple parametric plot. We need an expression for the x-coordinate, expression for the y-coordinate, and the range on which we want to plot. So for example, here the domain of our function. Here it tells us what our range should be. Our range should be a 3-tuple with the name of the parameter and the endpoint. So for us, that will be from -2 to 3. Okay, so let us make this plot. So simpy.plot parametric. We want to plot our parametric plot, so we need the x coordinate and the y coordinate, and we need the range, so t from -2 to 3. Hopefully this works. Let's see. And there we go. There we get our plot. And now we can read off, or we can match the information that we had before. So we start here at when the parameter is equal to -2, the point on the curve is 12 -2 over 3. So we start over here. That is our endpoint, or that is our start point. The next interesting point is x-intercept, which happens at the point 3 plus 4 times the square root of 3, y coordinate 0. So we start here, we move there, there's our x-intercept. It's not 10, not quite 10. If you work out this expression with a calculator, you will see it's 9 point something, but it's quite close to 10. Looks like it's 10, but it's not actually 10. Okay, then the next point happens when the parameter is equal to -1, and that is horizontal tangent. So horizontal tangent, there we see horizontal tangent. And if you think about what the tangent vector was here, maybe let's work that out. That is at parameter -1. So if we work out what the derivative of our vector function is at -1, the tangent vector has components -6, 0. So it points, if you think about a geometric vector, the tangent vector is pointing in this direction, pointing to the left, with an x-coordinate, or x-coordinate of -6 and no y-coordinate. No y-coordinate means that it is horizontal. So our curve goes this way. Here we've got horizontal tangent. Next one is the xy intercept, so it goes through the origin. Next point is another horizontal tangent. So here we've got another horizontal tangent, and then we've got that x intercept there, and then we've got a vertical tangent here, and then we move on to the end point there, and the end point there is -3, 6, and you can see here a -3, 6. There is our endpoint. So our curve is parameterized from this endpoint, goes that way, like that. Okay. So now we've seen how to use SymPy to make or to plot a parametric curve. Okay, I will see you in the next one.